Hello everyone, welcome to video 6.5. We're going to be looking at fraction division, but using the partitive model now instead of the measurement model, which was video 6.4. These two videos kind of go together because they're both dealing with the same type of problem, fraction division, just using different models. But if there were some questions from 6.4, they might carry over into 6.5. Especially relevant to the algorithm, which I mentioned in 6.4 we were going to address in this video, and so we will address that at the end. But let's get started. So before we get into dividing fractions using the partitive model, I want to go back and review the partitive model a little bit, because in order to use this model with fractions, we have to sort of reimagine it just a little bit. There are some differences in how we need to think about this model. So if we take, say, 8 divided by 4, then we know that that means that we have 8 objects, and we're going to distribute them over 4 different sets or groups. And so 1, 2, 3, 4, 5, 6, 7, 8. And so my solution is going to be how many in one group. And when we are using the partitive model with integers in this way, we have more than enough objects. We distribute them over several groups, and then we look and focus in on just that one group. In doing this model with fractions, it's a slightly different story, because we are a lot of times going to be given a problem where we don't have a full group. So if we were to have a problem like sorry, that was a straight mark there. If we have 1/2 divided by 3/5, then we're not going to have multiple groups to go back and look at that one. In fact, what we're going to have is 3/5 of a group, and then based on 3/5 of a group, what does one group do? So this is why I want to take some time to sort of like lay this out, that we're going to be talking about the same model from before. It's going to look a little different, but we're always going to come back to this same question: how many in one group? Just the way that we're going to construct that one group is going to be a little bit different with fractions than with integers. So here's our first problem from 6.4, which was our 2/3, I'm sorry, our 8/3 divided by 2/3. And we did that in the 6.4 slides by looking at it in terms of the measurement model and counting off these groups of 4/3. Now, in this partitive model, we want to know how many there are in one full group. And what this is going to tell us using this model is how many we have. So we've got 8/3. So we have 8/3 in 2/3 of a group. Using the partitive model, that's what this is going to tell us. So we can draw our 2/3. And so here's our 2/3. And so we've got 1/3, 2/3, 3/3. And our 8/3 has to be distributed over this 2/3. And again, one of the key ideas in talking about fractions is that we're talking about equal sized groups. So we can't put 5/3 and 3/3 in the two parts. They need to be the same amount. Now, one way I could do this would be just to simply split this up and make this 4/3 and 4/3 like that. That 3 is not very convincing. So 4/3 and 4/3. Or I could put in little tick marks to make sure that we can see. Here's 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, 7/3, 8/3. And so this is going to be very similar to the double number line version that we're going to look at shortly. Um, yeah. So we've got our 4/3, our 8/3, and so now what we want to know is how much is 3/3. Well, if each of these thirds along the bottom represents 4/3 here, then we know we're just going to sort of replicate this out. So now this is 9, 10, 11, 12 thirds, which we should recognize to be the same thing as 4, and we should recognize that as the answer that we got in the previous model as well, that we get 4 either way. That shouldn't be much of a surprise. 8/3 divided by 2/3 is 4, no matter which way we want to sort of like model and show the solution. But this is a different way of talking about it. We're not measuring off 2/3 at a time. In fact, there's hardly anything that we did with the 8/3 by its 2/3. What we did do is create sort of what's really a proportion in a sense. This 8/3 and this 2/3. And then, like I said, we want to know how many is in one group. And so this is sort of the conceptual difficulty in using this model with fractions. Like I said, we're having to go from having several groups and then dividing it, quote unquote, down into one group. But now it's almost like we're using multiplication to get to division. We have less than a full group, and so we're having to extrapolate out how many would be in one group. The same question, how many in one group? If it's a question, I should probably have a question mark there. So it's the same question, but we're just getting at it from a different angle. Let's look at this area model or this bar model for 2/3 and 1/2. Now, you might have noticed in the previous problem, does it make more sense to do that by measurement or by partitive? You know, I'll leave that for you to decide. I think a lot of people would probably lean toward probably the more measurement side because you've got 8 pieces. You're putting them in groups of 2 of the same size pieces. The common denominator probably leans it more toward a measurement model. We did this problem on the measurement as well, and we can see that if we do it partitively, so here's my 1/2, and I know that it is 2/3. And so if I want to find a full group, it's just going to be another 2/3. And so altogether, that makes 4/3. I would say that for this problem, because we're dividing by a half, this is going to be a lot easier just to sort of double that dividend to get the quotient. Rather than using the measurement model where now we have to go to common denominators and divide that out that way. So the reason I'm bringing this up is because I want to illustrate that certain problems are probably going to lean themselves a little bit more one way or the other. And so doing a wide variety of problems will very naturally motivate using a wide variety of models. There's a tendency among teachers to find the model that sort of makes the most sense to you and do a lot of that model. And then the model that either you don't like or don't understand quite as well or have a hard time putting into practice, maybe you don't do that one as much. But if that's the model that will resonate with some of your students, then you kind of have a responsibility to do that model as well. Just because it's not your favorite model doesn't mean it might not be the favorite model of students that you have in your class. So you have your preference, there's nothing wrong with that, but your preference should not supersede your proficiency, and you should have fluency in all of these models. We can flip this around, look at the 1/2 and the 3/5. So now we've got this broken into 3/5. So 1/5, 2/5, 3/5. And this gets a little bit trickier now because this whole 3/5 has to be 1/2. So we're going to distribute this evenly over these 3 sections because it needs to go over 3/5. So this is going to necessitate using equivalent fractions. So we need to be able to break this into 3 equal sized pieces. So my 1/2, I'm going to change into 3/6. And so now each of these will make 1/6. So the whole idea of multiplying it by 3 over 3 was so that we have 3 equal sized pieces. We can go back and sort of verify that this is the case. So 1/6, 2/6, 3/6 is the same as 1/2. I can see from an area perspective that this is all still very consistent, right? So now I want to go all the way out to 4/5 and 5/5. Got a little extraneous mark there. Let me get rid of that. So 4/5 and 5/5. So I know that each of these is going to be 1/6. And so altogether, 1/2 divided by 3/5 is going to be this 5/6. Again, if 1/2 goes to 3/5 of a group, then the question is how many to one group? And one group in this case makes 5/6. It's also worth probably pointing out that this is 0.5 and this is 0.6. So again, we have this smaller number being divided by a larger number. There's not going to be a full set of 0.6 in 0.5 to sort of use the ideas from the previous slide. So we should be able to recognize it's going to be less than a whole. So this is still pretty consistent with what we saw in the previous set of slides in estimating whether or not it's going to be greater than 1 or less than 1, using 1 as that benchmark. And again, we can think about this, we go even further back. This is a compound fraction. And so we know in this case that the denominator is greater than the numerator. And so we know this is going to be less than 1 using sort of our fraction reasoning as well. So yes, this is all very consistent with what we saw in the previous set of slides. So now let's go back and look at this using another application of the partitive model, and this is called a double number line model. It's not really any different than what we've seen before. You'll see that it's all very, very similar. This is a different way of sort of representing how these ideas are going to work together. And what we're going to do is we're going to construct a number line where we're going to have the divisor along the bottom and then the dividend marked along the top. So let's draw our number line. So here's our 0. And then we've got 1/3, 2/3, 3/3. And we know that we want 8/3 to be opposite this 2/3. So again, we have our divisor along the bottom, and we have our dividend along the top. And because it's a double number line, this helps to see these things being spaced equally. The area model should show that as well. I mean, all those areas should be consistently the same size. And so really this is just sort of a one-dimensional compression of that two-dimensional area model. So it's not really doing anything a whole lot different, but it is doing it differently enough that you'll definitely see students who one model will make sense, the other one maybe not as much, and then even for you, one of these may make a little bit more sense over the other. But it's always worth showing in different ways, different models, different ideas. They're not tremendously different, but different enough that it's certainly worth showing. So this becomes my 4/3, and just like along the tops of those rectangles that we saw, now we can see that each of these 4/3, 4/3, 4/3, and so this makes 12/3, which is 4, the same answer that we got before. We're just constructing it along this number line. And again, we're trying to get to this value of 1. Again, in partitive model, the question is always how many per one group. The same idea here, the 2/3 and the 1/2. Here's my 0, here's my 1/2, here's my 2/2, which is my single group. This is 2/3. And so I do the same thing again. This is 2/3, or add 2/3 to that, and that gives me 4/3. Oops, there you go, 4/3. So again, the same answer that we got before. Okay, I want to do a couple more examples of this, and then we'll look at the algorithm. So now let's look at 1/2 divided by 3/5. And in the previous problems, the divisor has had a relatively straightforward numerator. In this case, because the numerator is 3, we have to work this out a little bit differently with the double number line. So let's draw our number line. So here's my 0. Here's my 3/5. Here's my 5/5, which is 1. And I know that this is 1/2. It's going to be opposite the 3/5. Now, when we were dividing by 1/2, we could just double it and get to the whole group. Here, in this case, it's going to be a little bit harder to get there. And so one of the things the book talks about is dividing this to get to a numerator of 1. And so we're going to do sort of a two-step process here. We're going to divide by 3, and that gets me to 1/5. And so I can divide by 3 or multiply by 1/3. That gets me to 1/6, right? So if I were to take my 1/2, cut it into 3 equal parts, so now this is going to be 1/6. And you can see this is very similar to what we saw in the area model a few slides ago. Well, this gets us back to 1/6. And so now, divided by 3. So now I want to go from 1/5. This is where I want to get to. I want to know, again, how many is in one group. So to get from here to here, I'm going to multiply by 5. So to get to the 1/5 to the 5/5, I have to multiply by 5. And the same thing is going to happen here. I'm going to multiply by 5, and that gets me to 5/6. Again, the same answer that I saw before, just done a slightly different way. In the event that you're already at sort of a unit fraction here, then we don't need this first step. We can just go straight to the second step. If the numerator is something other than 1, then we're going to divide by whatever the numerator is, and then multiply by that denominator piece, and that'll get us to that unit. And we'll talk about what that means in terms of the algorithm here shortly. Now let's look at a slightly different variation on the previous problem. Instead of dividing by 3/5, we're going to divide by 5/3. It doesn't change that much mechanically about what we're doing. I'm sure you notice it's an improper fraction. It's greater than 1. So really the only thing that I have to kind of take any sort of precaution about is where my marks are going to go. So here's my 0. Here's my 1. We'll call this 5/3. And so now my 1 is going to be less than my divisor instead of being greater than my divisor like we've seen in the previous problems. Now, we're not dividing by an integer, so I can't just evenly distribute and do it as I would sort of an integer division problem, but the mechanism still works. So I want to get back to here, to 1/3, because I know once I get to 1/3, this is going to be fairly straightforward multiplying by 3 to get to the one group. So to get from here to here, I'm going to divide by 5, and that means doing the same thing here, divide by 5. And so if I take a half and break it into 5 equal pieces, then I'm down to a 1/10. So those are all tenths pieces now. And again, if you need, you can certainly draw a model for this. So here's my 1/2, 1/2, break that into fifths, and so now you can see that these are now going to be 1/10 pieces. So get to the 1/5. Now I'm going to multiply that by 3, and that gets us from 1/3 to 1. That takes my 1/10 up to 3/10. So my answer now in this case would be 3/10. I'm dividing a smaller number by a larger number, so I expect my answer to become smaller. And so that 3/10 is very consistent with that. So I've gone through all of this measurement and partitive model and kind of avoided the algorithm. Some of you may have sort of seen what was happening in the previous problem, that we're already starting to build toward that algorithm. In fact, all the steps of the algorithm are there. So let's take an example, an algorithm example. So let's say that we have A over B divided by C over D. If the algebra, if the variables are kind of confusing to you, you can go back to the previous slide and everything that I'm saying here will apply to the previous problem. So if you'd rather see it numerically, the previous slide certainly illustrates this. So we are at C over D, which I'll take to be less than 1, although it doesn't change anything if it's greater than 1. All the same ideas still apply. I want to get down to 1 over D. Now, if I can get there, then I know that I just have to multiply by D to get to 1, because that would be D over D. So for here, I need to divide by C, which is the same thing as multiplying by 1 over C. So if we take these two ideas together, we combine them into one product, so multiplying by 1 over C and then multiplying by D is the same as multiplying by D over C, which is the algorithm that most of you already know. So if this was my A over B, once I divide this by C, then this becomes A over BC. And then once I multiply it by D to get to the one full group, then I get to AD over BC. As I mentioned in this class a bunch of times already, I'm not anti-algorithm, but I am anti-algorithm that's not connected to some sort of understanding. So this double number line or this area model, we can use this with certain special cases that work out nice and easy, build into cases that are a little bit more complex, and then eventually we start to generalize this process out until we get to this actual algorithm. The algorithm should be the payoff. It should be this thing at the end that allows us to generalize all these concrete steps that I've done. It should not be the starting point. Here's how you divide. Just do this and don't worry about it, where students now can't understand why they're doing any of what they're doing. This is not that complex of a mechanism. This double number line isn't that complicated. It looks a little bit more complicated as I've done it algebraically. I can do it numerically. If you go back and like I said, look at the previous slide, you can see the steps that are there that I've divided and then multiplied. And so you put those things together. You've multiplied by that reciprocal. You've multiplied by that. It's all the pieces are there, right? I don't think this needs to be proven rigorously necessarily. This can really all kind of be done in one step to just say that A over B over C over D, you just multiply it by D over C times D over C. This all cancels, and there's your multiplication by the reciprocal right there. You can explain this rigorously by talking about reciprocals always having a product of 1 and et cetera, et cetera, et cetera. There's a time and place for that later on, right? A proof, quote unquote, that convinces is going to be more than enough without having to get into a lot of the rigor of why this works. But I want you to understand why this algorithm works, how to show that the algorithm works, and be able to explain to your students why the algorithm works. So if you're a checkpoint, I want you to look at 1/3 divided by 4/5. Same thing as the previous slide. In 6-4, you should be using the measurement model for that problem here. Obviously, once you use the partitive model, whether you want to use area or double number line is up to you, but I certainly want you to use one of those two models. If you understand one, then I would challenge you to use the other one as well. If you have any questions about anything from the slide or anything from class, please, by all means, bring them to class and we'll get your questions answered. All right. Thank you.